In this video, I want to introduce some of the key concepts behind monocular visual odometry pipeline, which I don't really have time to talk about during the in-class presentation. So the first step of the pipeline is, of course, camera calibration. So I'm using a chessboard of known dimensions because this is compatible with the OpenCV calibration pipeline, which requires you to give the size of the chessboard you are using, and the OpenCV find chessboard corners function is able to detect all these corners in the image and then process it, which gives you the camera matrix. So how this works is basically you give the world coordinates of each of these corners on the chessboard, the world coordinates. So here I'm using this left bottom point as the origin of my world coordinates, right? So subsequently you can calculate all the coordinates of these corners on the chessboard. So, and also, of course, using the photo I take, you can figure out the pixel coordinates of these corners, of these same corners, right? So as we talked about in Professor Ying Wu's class, the camera matrix is nothing but the transformation between the world coordinates and the pixel coordinate. So the previous information can allow you to construct this equation, which you can then solve for this matrix, which is the camera matrix, rather easily. So the next important concept, one of the most important concepts, is of course the epipolar geometry. Because we are doing the 2D to 2D case, the epipolar geometry is of the greatest importance. So as this figure illustrated, the first process in solving this epipolar geometry is, of course, you want to extract a large number of feature points, which is point P1 on this frame, and then on the next frame you want to find the pixel coordinates of the same set of feature points you extracted in the first frame, right? So then you can construct a relationship between these two set of feature points using by somehow manipulating the difference between the pixel coordinates in the first and the second frame, right? So what we want to solve for is somehow getting the rotation matrix and the translation vector from camera pose 1 to camera pose 2, right? Because we are observing the same set of feature points, which have the world coordinates of point P here. So the first most important observation is that the point 01, point P, and point 02 are on the same plane, right? So using the basic geometry, we are able to calculate the plane normal of this 01P 02 plane, right? And one of the very important property of plane normal is that if you cross product the plane normal with any vector inside this plane, the cross product is going to give you 0, right? So that's why if you see this equation here. So let me briefly explain how we get this equation. So the first thing is to find a point that's never going to change. so that we can construct equality between two expressions of the same point, right? So here, the point that never changes, of course, the world coordinate of point P, right? So K here is the camera matrix, and KP here gives us the image coordinate using our camera model. And of course, if we treat R and T as the pose transformation between pose 1 and pose 2, we are able to express the feature point in frame 2 using this expression, right? So, and then this is doing this basic inverse operation. We are able to arrive at this equation. And one of the most important trick happens here, which is multiply both sides by this quantity. This quantity is actually, so this is different representation. We can also think of this as cross product T on the left side. Which is allowable, right? Because we're doing this on both the left hand side and the right hand side of the equation. So this is how we get this equation. So the trick happens here is that this vector, the plane normal, is actually orthogonal to both T and x2, right? Which makes the left hand side 0, because we're doing a cross product between a vector that is in the plane and its planar normal, right? So this is why we have this equation. So again, if we want to construct the equality between the image coordinate P1 and the image coordinate P2, we can just sub in P1 and P2, right? The x1 is equal to K inverse P1, and x2 is this, right? And so here we get the famous epipolar constraint, right? So the next step is to solve for this essential matrix E. So all those steps I just described is implemented in the OpenCV's find essential matrix. So you give the feature point coordinate in the first frame and the feature point coordinate in the second frame, and of course the most important K matrix, the camera matrix. And the reason we have a ransack here is because we want to filter out the outliers in the first and the second frame, because the feature detection and the correspondence may not be very accurate, and we may have some false correspondence. So we want to remove those outliers. That's why we use the ransack algorithm to filter out the outliers. So the next step, this recover pose, what that is doing is just we want to perform singular value decomposition in order to get the rotation and the translation matrix, right? So, and one complication we have here is that we may have different solutions to the singular value decomposition, and there's only one reasonable solution, which means the point P is actually in front of the camera, and all other solutions will say that the point is behind the camera, which doesn't make sense, right? So we want to choose the correct one, and the recover pose function in OpenCV does all those steps for you. Alright, so this is all we need to get the transformation matrix from camera pose 1 to camera pose 2. So in order to get the entire camera trajectory, you can just, stitch together all the rotation and translation you have, and then this is the result, right? This is really quite straightforward. So the next important concept I want to introduce is the bundle adjustment. So let me find the textbook chapter for this. I haven't successfully implemented this part yet, but I think understanding the rationale behind this is going to be helpful. Right. So basically, what the bundle adjustment is trying to do is trying to improve our estimate of the camera poses, right? That way we can get a much more accurate odometry information. So bundle adjustment achieves this by solving this nonlinear optimization problem. Let's switch to another slide. Yeah, this is the slide from Tübingen University's computer vision class. So as you can see here, this optimization problem actually optimizes over these two sets of parameters. So xw is the world coordinates of the feature point, and pi here is actually the projection matrix, which contains the intrinsic, which is the camera matrix, and the extrinsic parameters, which is the camera pose r and t. So after we solve for this optimization problem, we are able to replace our original visual odometry results using this optimized pi parameters, because it gives us the improved version of camera rotation and camera translation, right? This is really straightforward. But a complication comes when we want to actually solve this nonlinear optimization problem. So this entire chapter is actually dedicated to solve this nonlinear optimization problem, right? So let me see. Some of the details that is going to be helpful is, right. So you may ask, where does the visual odometry result come in the bundle adjustment pipeline, right? So for every optimization problem, we need an initial guess, right? So in order to obtain the initial guess, we can use the camera rotation and camera translation vectors we obtained in our previous visual odometry result. So we can use our result from VO to use them as a initial guess for the bundle adjustment optimization problem, right? Yeah, let me see what are other concepts I need to introduce. Right. So I find this really helpful library that has some previously implemented solvers that is dedicated to solve the bundle adjustment problem, because there are some interesting matrix properties involved in the bundle adjustment process. One of them is that the matrix is actually sparse, meaning that most of the components of the matrix is actually zero. So this is able to help us a lot when solving the nonlinear optimization problem. So yeah, they also offered a very helpful Python example, and I think my next step for this project is to somehow change this template and try to see if the bundle adjustment method is actually able to improve my monocular visual odometry method and result. Yeah, I think that's it. Thank you.